Before we go much farther, let's talk about some sample uses of polar coordinates. Here's the list, but I'm going to show you some web pages. So if you haven't seen the movie Hidden Figures or read the book, I really strongly recommend it. It's got lots of great math in it. It's got interesting race relations from U.S. history, which you can imagine how fraught that is. Here's the movie poster. My 7-year-old daughter said this is her favorite film, and I think it will be yours too if you go take a look. One of the mathematicians in the movie, I mean, this is just the actress. I'll show you the real person in just a sec. Katherine Johnson. This is a picture of her actually at work. That is an old-fashioned adding machine right there, and look at what she has here. It's a literal spreadsheet made out of a spread out sheet of paper. In the movie, I don't want to spoil anything, but they're talking about publishing a technical note, and here's her name on it. That's actually a plot point in the movie. And let me show you some things from the technical report here. Look, they're using one of our favorite trig identities here. Here they're using basically a Taylor expansion or a tangent line. And then here they're talking about stuff that's basically Newton's method. Not all calculus courses get to cover Newton's method, but it's pretty important. And then here in another section of the report, they're doing things with r and theta, so they're using polar coordinates to think about where the satellite is relative to the Earth's center and all kinds of interesting stuff. Other uses for polar coordinates involve electron orbitals in chemistry, mostly quantum chemistry, so interesting patterns like that. You can also see polar coordinates in use if you're looking at directionality of microphones. Omnidirectional means it's good in any direction, but maybe you want more sensitivity toward the front of the microphone and less toward the back. So you might be talking about a cardioid shape, and we'll look at some of those, and then alternate versions of those, and then some that are super sensitive to the front, not too sensitive to the sides, but then kind of accidentally have some sensitivity toward the back of the microphone. So that's microphones. You can also do the same thing with antennas. You might have seen radio antennas that look kind of like this. That's called a Yagi. And you can say, how sensitive is it directly ahead? How sensitive is it directly behind? How sensitive is it off to the side? You can even do that in 3D. Speaking of 3D, the Navy, US Navy, does all kinds of antenna sensitivity studies. And instead of paying money to put an antenna on a ship and test it out, they actually build a little tiny brass, well, not tiny, like a meter long brass model of the ship and put a scaled version of the antenna they want to build on that scaled ship. Then they put it on under this big gantry, and they have antennas that they can move around and test how much electronic power is coming at all different directions. Here's a close-up of that process. So I guess that's about a 2-meter long brass model, and they put realistic antennas on it, and here you can see the antenna mounted on the gantry that's going to sense how much electromagnetic power is coming off at different angles and stuff. And if engineering isn't your thing and biology is, boy, have I got an application for you. It turns out that bees actually communicate to other bees using polar coordinates. They say, okay, here's how to find the food that I just found. They'll do a waggle dance in the hive where they circle around and then waggle back and forth to indicate what angle from the sun to fly. And the amount of waggling they do tells how far out to go. That's the radius. So bees are a lot smarter than we would think, right, using polar coordinates.